So everyone see my screen?
Yeah.
Cool. So I wanted to say firstly, thank you a lot, Stefan and Mark, to give me this opportunity. I worked on self-studying like deep learning for some time, and I really wanted to challenge myself with like preparing something, break down some papers, because I didn't have so much experience with that, and I wanted to tell like in advance that I'm not like cool computer scientist. I have physics background, but I'm really interested in all this stuff, and I wanted to tell like if I'm explaining something wrong, just tell me. It would be so beneficial for me, and like no problems with that. So what I wanted to talk about today is some key ideas behind linear RNNs and space models. As sorry, somebody has questions.
Physics background, yeah, I will have, I guess.
Oh, okay, no problem. So, first of all, I wanted to do some reasoning why I choose this topic and why it's why any other models than transformers are even interesting now, because actually it is natural thought that like if transformers perform so well, like we have GPT-4 and stuff, and why would we need anything else? And that's why I wanted to discuss really briefly like some issues we have with the transformer, and why scientists actually thinking about like what else we can do, and why it could be cool. And the first problem with transformer is that transformer is actually not a sequential model, and this issue is partly solved by positional encoding, but that kind of encoding assumes that the sequence length is fixed, so that you have the right resolution, and otherwise you lose resolution or might lose information about the topology of the space or stuff. And you have some issues sometimes with judging contents length and inference. And the second point here is it is not Turing complete. And actually, I found for myself this Turing completeness thing interesting in this context, because we always see all these messages somewhere on LinkedIn or Twitter, like people saying that recommended some stupid stuff, like they tried to solve some equations, they could convince LLMs that like 2 + 3 is 5. And what is important to understand that actually LLMs are not made for performing for executing like any algorithm. And what is cool about yeah.
I just want to jump in. I saw a bit of an ICML talk. I'd have to dig up the paper just to bolster point number 2, which is that they were testing like the reasoning like complexity that the different LLMs can do, and trying like experiments with fine-tuning very small ones. I found that like GPT-4o, for example, was only able to get complete reasoning sequences up to 10 steps. And you can extend it to like chain of thought or agentic stuff, but like it could only do straightforward like reasoning within 10 steps. And they're able to train much smaller models that are like deeper, that could do more, up to like 30s or so, but 30 is not a lot. So I like this point.
Yeah, I like this point because for me it was like I always wasn't convinced that we are really close to artificial intelligence with LLMs. And for me, like this Turing completeness thing was interesting, and I have actually a slide about it, like on Turing completeness of modern RNN architectures, like both RNNs and transformers. And actually, why people think that RNNs could be Turing complete. When you think about Turing completeness, like it's this thing about your endless strip and some controller, and RNN is very naturally comes as this controller, right? But actually, like a Turing machine, it's just the description of Turing machine, but from where the idea of Turing completeness of RNN comes from is like unlike other architectures in RNN with limited memory, you can like provide an unlimited number of data inputs because you provide them recursively, and you can transmit a theoretically infinite amount of data piece by piece. Therefore, it is Turing complete. Kind of Turing complete, and it's like an embodiment of Turing's endless strip. But actually, for real, both for transformers and RNNs, they could be Turing complete with some adjustments. And there are some papers on that, like if you need infinite memory. So for both, you actually need infinite memory, and they both could be Turing complete. But the problem is that it's not really possible with all we have today to provide this infinite memory. But I just wanted to mention, if you need infinite memory, then you can expand RNN to real infinite numbers, like not floats, but real numbers. And with transformers, the equivalent transformation is to create endless context window, which is obviously not possible. So both RNNs and transformers become universal only when they have infinite memory. But yes, people talk about it, and knowing that GPT-4 can compute cannot really even compute n factorial is a bit disappointing, but it cannot do it just by its architecture. And okay, it's about providing guarantees. The third point, like generalization bounds, are useless at the moment, and actually, this idea assumptions break down on scale on generalizations. And fourth point was a bit surprising for me, maybe because I didn't have so much experience, that softmax is not a real good activation function. And actually, I borrowed it from the presentation of one of DeepMind researchers who worked actually on Griffin paper, which I want to also discuss today. And actually, in his slides, it was softmax is a horrible function. And I just made it more gentle. And if the reasons are softmax likes unimodal, Vino takes all dynamics, and softmax iterates, not allowing gradients to flow very quickly. And that's why actually it's not so good. And the point he discussed a lot also, that we don't really know that transformer architecture is so good itself. So much better than RNNs or SSMs, but the coolest thing in transformer is actually the parallelization. And I can not give any strong opinion on that, but his opinion is that if we could have that it's the key in transformer, and even attention is not such a thing, but this parallelization. And while linear RNNs are cool, because I will talk about how we can parallelize it. Okay, so I think I am taking too much time for 2 slides. So next I wanted to discuss really briefly recurrent models, their positives and negatives. And positives, it's natural and compact choice, very natural, because we know that our brain is recurrent. And we have this fast inference. I will not go through all these points. I will share the presentation then. So provable expressivity and negatives, and it's 2 negative things that actually are overcome in linear RNNs is strain instability. All we know about this exploding vanishing gradients problem, which actually made RNNs not possible for usage. Actually, they were more a theoretical model for a long time, before LSTM was introduced with gating and long memory, long short memory, which fixes this issue. And training scalability and expressivity bottlenecks compression and optimization, where our current layer uses the same amount of compute as convolutional layer, that compute cannot be parallelized across multiple processors. And even if you have a lot of processors available, you can begin evaluating the neural net on an input until all of the previous steps have finished, because you need to feed out like previous step. And we will talk this ahead. This we discussed. So why Mamba? I wanted like to have first slide like why Mamba is interested. Like Mamba is actually the most famous model from state space models family, and interesting thing that it can be introduced both like as extension of state space models and extension of recurrent neural networks. Actually, state space models comes from control theory, which is not something like every person have knowledge about, and that's why it's much more natural and easy to introduce it from this recurrent neural network. And actually, as it was like my first time diving like into a lot of papers and talks on AI, I was a bit surprised. Like quite often, researchers tell about their model something like, it works, but we don't really know why. And as I am coming from this physics background, like in physics, you don't have such stuff like if something works, you can see by your eyes that it works. And like if you see the math, like it is obvious. But I think it's because computer science is so different, because it is made by humans, and it's good. So why is Mamba a good idea? Mamba uses less compute than transformers, and for an input sequence of 1 word, Mamba uses only ONN computer, whereas transformers use n squared, because Mamba can be introduced as extension of linear RNNs. And so we are now going to linear RNNs, and as I already mentioned before, linear RNNs should solve these two issues, like stable training, so exploding and vanishing guidance issue, and scalable training. So we need to know how to parallelize linear RNN. So we see there like questions for RNN and linear RNN, and it's actually quite an intuitive thing here, because we just like get rid of introducing non-linearity here. And it could natural question is where the expressivity comes with that, like how we can know that it will even work. And we can make up for losing expressivity by applying a full neural net to each output vector afterwards. This is similar to how in transformers you can apply the value neural nets with simple linear function, and then add the neural nets in between self-attention layers to make up for the lack of non-linear processing power. So just like in transformer, we will alternate like linear count layers with element-wise neural networks. Yes, so now we will talk about like how we will actually parallelize linear RNNs. So we have the equation, and if you think like where is Wx here, it is just like inside this yi minus 1. And so half of the parallelization is introduced here, and it is through scan. It is also known as like perfect sums and associative scan. And the slide is strange because I thought that I will not do it, but in the last moment I thought that it's better to have it. Like how it works, like if we want to have a sum like of this arrow numbers, and like can just sum everything one by one, but like in a associative scan, like you just first like sum the closest neighbors, then these ones, and these algorithms have like when the step size is the size of the input, each output contains the sum of all previous terms as desired, and it's trivial to see that each iteration can be computed in parallel. However, the different iterations do still need to be computed sequentially, and there are like log n iterations. So if you have n processors, you have the complexity of log n. And Actually, here we are doing it for some, but it is true for our associative operator. And what is actually associative operator? Like it's any operator where where you change the order of operations, the result is not different. Please fix me if I'm not right here. And this operator comes from actually this equation. And we have this V2, V1, because as I told, inside of this one, we have this. And it is an associative operator, like it can be proved. And that's why we can parallelize it with this scan as well as sum operation. And the issue here is this W into the cube, because it's actually a lot of operations, and doing that, if in RNN, what we are doing, we just we have our hidden state, if we multiplying it, and it's actually is not so expensive as this thing. But we can fix it with the diagonalization, and the matrix can be I don't know. Sorry, I have never talked about such stuff in English. Diagonalized, and and we have our matrix, like diagonal matrix and inverse matrix. And why it is cool? Because when we compute now W squared, this one and this one collapse, and this one too, and we just need to we just need to have diagonalized matrix squared. And what is important about this diagonalized matrix is that only on main diagonal we have the elements, and all other elements are zeros. So it's actually not super expensive operation. So when you multiply the matrix by itself in this form, the inner pair, inverse, and pair terms cancel, and the product of two diagonal matrices is just the diagonal matrix with the product of elements. That is in order to compute and this squared, all you need to do. Okay, I have already told all of that. And here we are just you just see how it is. How we have it now, we first apply a complex matrix P to the input vectors, and then perform the linear occurrence with the complex weight vector W using element-wise multiplication, and finally apply by minor rows to the output. But what is important here, actually we don't, it's quite expensive to compute this inverse matrix. So instead of that, we just have some other different matrix, and it's actually even make again inexpressive to all of this algorithm. Okay, I guess now we are we completed this with parallelization. So it's how we will parallelize this linear RNN, and now our issue is with gradient vanishing and exploding gradients, and how we will fix it. RNN gradients are stable so long as the recurrent weights are 1 and the inputs are 0. So in the linear RNN paper, the authors proposed to initialize the linear RNN in the set stable state. And to do so, they parameterize the weights in complex polar, you can see it here. Here they just show you what is the complex number in a complex polar, and here they show you can see here that when you have this e to the power of minus e, and it will always around 1, because when e to infinity it would be just 1, and here they also initialize it around 0 and p divided into 10, and with this parameterization, with this, it's also important that here we have, as I told before, like the input should be around 0. That's why what they do, they also parameterize like here. When x1 is going like into our network, they also multiply it by delta, and we can see here that this spin, like e to the power of minus e to the a, will always go to 1. So all the spin will always go to 0. So this vector we are feeding to our RNN will be always around 0. So we will still be in the stable state. Please let me know if I explained it fine, because I think it was very messy. Okay, no questions, so I hope everything is okay. State space model are near RNNs. So actually, with different parameterization. So state space models, yeah.
So was this the last slide? Was it addressing like the vanishing gradients problem? I didn't fully get that.
Yes.
So in a nutshell, what was the trick there?
Because it is like in this, it is in this stable state, like you like when you are but like in RNN we always have the same weights, right? And why we have this problem of vanishing and exploding gradients, because we have always the same weights, and like when we backpropagate it, if the weights are little, we have vanishing gradients. If the weights are too big and our gradients are too big, it's exploding. And but if all the weights will be always 1, we don't have issues. That's why it's stable state. And like when we are feeding the networks like 0 vector, it always like don't harm the system so much. That's why it is a stable state.
You want to have weights close to 1, or?
Yes, you want to have weights close to 1.
Okay. And how do you guarantee this?
We guarantee weights close to 1 through this parameterization, actually. You see here, these weights are a to the power minus a to e, and it will be always on the surfaces this uniform, like to parameterize the weights in complex polar form, like a to the power of e, and where a is the magnitude and b is the value, and then restrict the magnitude to be less than 1, and which always outputs a number between 0 and 1. And instead of randomly like sampling from normal distribution, like we initialize it, so it always will be between these numbers, like it not always 1, but it's like between 0, 9, and 1. It is mentioned here.
Okay.
And it says there's no guarantee that it's not going to destabilize. It looks like the third bullet talks about one way to maybe help avoid destabilization, but it looks like, you certainly could throw this off, but it starts in a stable place.
Yeah, actually, like we cannot like do guarantee, but like up to the model, like being training and the weights change, like there is no guarantee that it will remain stable. But in practice, it appears that just initialization, like the model like this, is sufficient to allow it to learn to remember context for tens of thousands of steps, which is enough for like the case they used here.
Yeah. So my understanding here, right, is generally right for transformers and deep neural nets, right? There's a famous paper from Gloro, right, where they talk about doing normal distribution weights, right? I can you can find that, dig that out, the famous line there, and that basically is one of the main things that really help people make big progress in deep learning, was to use this sort of normal distribution weight, Gaussian distribution, and that's basically saying that works great for deep nets, but we need this other initialization scheme, right? Because we don't want the same initialization to be able to train on for these recurrent nets, right? Where you want to have them be in this kind of in space, be the sort of, I say, circle between very close, just around the ring, right, and kind of the space rather than kind of the normal distribution.
They're Gaussian distributed. They're just Gaussian distributed around a very small range.
Around the ring, right? Yeah. So I think that. So yeah. So I'll post the global paper, but basically, I think that's my understanding of this. Basically, right? Is basically it's saying no, like, don't use that. Use this is how you have to modify it to be able to properly initialize your RNN. Otherwise, you get these very big. If you have the other things that you sort of, if you don't, then you get these kind of things that are out, and then it explodes or clips the gradients, right? If you have these things which are sort of initially outside that space, right? So you're kind of, and that kind of makes it very difficult, right?
The slide says normally uniformly distributed, not Gaussian.
Yeah, so it's uniformly right. So.
It's very inconvenient for some reason. Like I don't see any of you. Maybe I don't do it.
It's tough. It's tough when you have the presentation because it has the screen in there, and so.
So when you're presenting the screen, you cannot see people.
Yeah. So sometimes people use like a different device and something like that. That's something people. Yeah. No, it's tough.
Okay. I thought maybe I'd do something on. Okay. So we will go to the state space models. And for the state space models, like it's actually linear RNNs with a bit different initializations, which prescribed by this control theory. And in the linear RNN paper, they evaluate this model on the long-range ARENA benchmark, which is a collection of 6 synthetic tasks that evaluate a model's ability to perform long-range reasoning. Like, for example, in the past, X-like tasks, a model must classify images as whether or not they contain a complete dotted path between like 2 circles, and it's example of that. And except that the image are flattened, in 60,000 pixels. And here we can see that like linear RNNs here outperforms RNNs and transformers. But while linear RNNs do perform really well on the long-range ARENA benchmark, this doesn't mean they are good language models. Like for language modeling, linear RNNs perform way worse than transformers. But actually, this hash3++ model is a state space model, and it's like second best behind transformers. And then Mamba was introduced. And in the Mamba paper, it was identifies that like the problem with linear RNNs, the linear RNNs are incapable of selectively forgetting information from the output vector. And if the values are close to 0, then output vector will be set to 0 after every point. And effectively, the model will always immediately forget whatever comes before the current input. And if the current weights are close to 1, then the output vector doesn't change when it's multiplied with the weight. So the output vector will accumulate information from all inputs observed. And what you want is the model to be able to decide when to store information and to forget. And the solution in Mamba is like instead of using the same weights in each step, actually like the things that everybody didn't in previous slide, like use different weights which depend on the input. And Mamba implies like a linear function to each input vector to generate a separate weight vector for the input. And then the recurrent scan is performed using these generated weights. And this way, certain inputs can generate weights close to 0 and thereby erase information from the output vector, but other inputs can generate weights close to 1 and thereby like leaving the output vector unchanged. And yes. And actually there are like this high performance. Yeah.
Sorry to interrupt. I think this is a very important point in general, right? Like, the really, like, the big thing is input dependency, and a lot of people don't realize it when they study the transformer architecture in the beginning. is that the power of transformers, like, yes, it's order of n square, and it's like, squashing all tokens in a fully densely connected graph pairwise. And it doesn't have the problem that in RNNs where, as sequence length increases, it's hard to encode all history properly. But one of the big, humongous leaps that the transformer architecture allowed is the networks. So for example, like take a CNN or even a regular RNN, right? What happens is no matter what, once it is trained, the weights have been learned, nothing else changes, right? Like the transformer architecture is static. Whatever comes in flows through, feed forward, and output comes out. Nothing is dependent on the values of the input, right? Like it's a gigantic weight network and goes through. Whereas in a transformer, it's obvious when you say it, is that how things are combined in the self-attention layer is completely dependent upon the content of inputs, right? Like depending upon the sequence of tokens that it is combining or mixing, it will do it differently, right? Like, based on the weights, the computed will be completely different based on the content. And this input dependency is very important. It turns out for language modeling and for any long horizon sequence tasks, not in Google long range arena. Long range arena is actually poorly designed. Its design is not very good for being good on long range arena. Doesn't mean you will be good on language modeling, right? And that's why their whole H3 Hippo, Hyena, all these papers came out because they realized that their SSM was not doing well on language modeling. But really, this part, this slide is the key, right? Where they are getting they are using the simple trick from transformers to make things input content dependent and maintaining the linearity of RNNs, right? Like, so they're bringing the niceness of RNNs, like infinite recursion. Your memory is not blowing up, not order of n square anymore. It's n log n, and you are now input dependent. Without this input dependency, Mamba won't work.
Yeah, I totally agree with you. And even I have on my very last slide this delta rule thing. It's related to linear transformers, and it's actually even going from this fast weight programmers, which is the first paper which actually introduced kind of transformer. And why I added it here, because I thought that it's very like this trick in Mamba. Like delta net allows for memory conservation. Like if you add something, you must remove something. And actually, if to describe it easier, delta net is a version of linear regression. Like you train a model that is essentially a linear regression model, but instead of calculating gradients for it, you train a network that attempts to predict gradients for the input, and the algorithm enables you automatically manage a fixed amount of memory. And therefore, unlike traditional transformers, we can deploy it in robots, maybe in phones. It's promising thing. And I just didn't break it down too much, but
nice.
Okay. So we will continue with this high performance memory thing, and in standard RNNs, output vectors are the same size as the input, and Mamba expands the size of the output vectors to a factor of 16. And just nice to know. And okay, so here we can just take a look at how it performs around everything else, and we can see that it's here, and here we have the transformer, and computational complexity is n log n from all which we discussed before. And in the context of large language models like GPT-4, I feel like I missed the slide or something. Could be. So here I already begin to discuss actually the Griffin architecture, and here is it. And here we are talking about why they use sharding, and they use like multi-regression sharding, and also from the talk from the guy who released this article, he told that it's very important like to think about scalability first when you are only like planning your architecture and not afterwards, because you will quite possibly run into issues. And in the context like of like, okay, the block that you want to shard like needs to have an even number of layers, and usually people prefer it to be 2 layers, and this graph illustrates like how the operations work. The blue represents one device and the orange the other. And if you split the weight matrix center a certain way, you won't need to communicate between devices except in the end. And actually, the diagonalization thing that we saw before is kind of important here, because sometimes with sharding, because actually when you have this diagonalized matrix, you have like all the values in your Jacobian, you can like you can see all of them easily, and it makes like this separation while sharding easier. And okay, this is a start to think about scalability from the beginning, and it's Megatron sharding, which is used actually in Griffin. And it's just breaking down like all the blocks and what was their motivation, like why they. So here we have this parallel linearies, and they use this like popular Gil block, and also like element-wise multiplication here. And why they use this temporal cone 1D, because like it worked very well and before, and it was first introduced in this, sorry, I kind of got tired a bit, in Hungry Hippo paper. And actually it is grouping like together tokens, because like in previous papers that shown that first layer of a transformer tries to group pairs of tokens together to make kind of a data set for which for you doing context learning, and that's why they put it behind this one, because this thing actually will perform gating, and here you can choose your like recurrence, and they choose like just linear recurrent unit. Okay, it's actually the same thing that we had before, and here's here they tell that also they used it's about diagonalization again, because here we could have like just S4, but they replace matrix multiplication with element wise, and like dense matrix moved to diagonal one. So diagonal one is this one, which is reduce the number of blocks and allows like things to be shardable, and it's what I already told here. So the stuff being shardable and the diagonalization are connected. And here it's actually was this slide was the argumentation why they didn't use just this S4D, because it even performed worse than LSTM. And instead of that, they use they also they also introduced the gating here, and we can see it's like quite complicated thing, but you can see that here we have input gate, here we have something we already saw before, like in Mamba and in linear RNN. There we have this recurrent rate and some learnable parameters. And this is the formula for the LRU. The important thing to note is that also it looks complex. It's exactly what we've discussed before. And the only novel part here is on the left, the input gate. And we chose to add this gating because without it, it didn't perform well. And I think I forgot the slide where it actually performed as well as LSTM with gating. And here it's like the last slide. We see the performance of all the models, and actually like Hawk is just like a linear RNN, and Griffin is a model where also attention was introduced, and we can see that while Griffin, so we have here two tasks, and the first task is generalization to longer sequences, and like both model doing quite good on that, but on this one, it was some task like to find a telephone number or and induction heads task, and this Hawk model, which was without linear attention, performs much worse than the one which is actually a hybrid model. I know that you already discussed it on this meetups. So okay, and it's actually the delta rule thing. I think I maybe didn't tell enough actually about this too. But yeah, you can take a look here also, and maybe I can go into results. Like this work introduced Hawk, our current model incorporating an overgated linear recurrence layer and the GLRU, and we also introduced Griffin, a hybrid model which mixes the GLRU layer with local attention. Like like I said before, this is Griffin, and it performs like better on these like RAG tasks than this one, exactly because it has attention, and this actually is the reason why they chose to introduce it, because they saw that it performs very bad on this like lookups tasks. And this model demonstrates exceptional language modeling performance across variant scales with held out loss exhibition, power loss scaling, and compute resource increase. Hawk exceeds the reported performance of Mamba on downstream tasks when trained on half as many tokens, while Griffin slightly exceeds the performance of Llama 2 when trained on over 6 times fewer tokens. Furthermore, empirically validates the inference time advantages of Hawk and Griffin and observe reduced latency and significantly increased growth compared to our transformer baselines. So yes, thank you for your attention. And if you have some questions or if you want to go like back to some slides, just tell.
No, I think that was very it's very interesting to see all these tricks, right, about and parameterization and actually going through and explaining why you pick why they like it's kind of like a whole like so both like all these things about like actually how you do the training piece, which is always very interesting, but people don't actually tend to I said like this there the goal it's actually these like how you actually solve some of these problems and all this kind of things you need to actually solve to get a new architecture to work. And so it's nice to see the kind of whole history there of like, here's how you do initialization and here's how you have to do these parameterizations and get the scalability. So that was really interesting. And also, when you have the chart there and having going through and explaining, here's why we picked these different blocks. Too many papers I see are like, like the one from Snowflake, which is like, we just threw a mixture expert in here and it worked. We didn't tell you why. Yeah.
Right. Like, their architecture makes no sense. Like, oh, we did everything. It's not even like this hybrid, like, oh, here we have this one expert on the side and then here's the main one. And it seemed like novelty for the sake of novelty. It was not, but Alina, one question is, what after reading all these papers, do you think like, okay, so I'll tell you, like, some criticism of all these line of work where people say that, like, okay, it's especially in all the scaling up experiments, they find that it's very tough to beat just the vanilla transformer, right? Like, even today, if you see like Llama 405B, it's just a simple dense transformer, right? Like, and pretty close to the vanilla one. Like, maybe the things that have worked is like, grouped attention, group query attention heads and whatnot. But overall, the architecture is very similar. Do you, and people have been wondering, like, why are we not going for like these new architectures where we can now solve like all our KV caching issues and order of n square problems? Do you see that, like, GPT-5 or 6 will be like, let's say, a Mamba style model or a Griffin style model or something very different from a vanilla transformer today?
I think actually all this thing with linear transformers, like linear RNNs, is more towards like making like more little like scalable models, like for, as I told, like for little devices, than to actually perform the transformer. But actually, it's there is something like flash. We have flash attention, and it's like new paper called flash linear attention, which is also like quite good. And I don't know, like I heard actually from people that they say this thing like about actually this fast weight programmers, which was kind of that it was like even better than actual like attention is all you need paper, but like it was just like a wrong moment. And like what I often heard and like read that. People I find that maybe we will go back like to what was introduced there than our actual transformer, and maybe like to get rid of softmax somehow, maybe, I don't know, invent a different activation function. But actually, like a close friend of mine is working like in this Jürgen lab in Swiss, and they find this like delta rule thing like very promising, and they are convinced that it actually like will be the next Llama. But when some lab is working on some certain things, they are of course more inspired. But the insight is that quite possible.
Yeah. Okay. Fair enough.
I do think it's also, I think one of the things here, I think, is all these things here, it'll be interesting to see whether you get, for example, like something like text-to-speech, for example, which is very linear, right? On some of these things here, right? So like text-to-speech is very linear, like audio is very linear, right? Tends to be. Well, images, like image CV, like things like pixel, like these kind of like trying to do sequence-to-sequence learning on images is very tough because you have to go through the bottleneck and, kind of thing there, and kind of like language in the middle. So it also just might be that you start seeing, to your question there, I might be curious, you might see like the audio part. So if you talk about something like, is it that? There's a chart that tries to do like, basically wants to replace text input with audio input, right? And have audio in and audio out. Then you might have this type of RNNs might make very nice fit there, because you could then, and so you might have the audio piece in there is using this type of architecture. Well, look at the image piece might be using,
like a hierarchical transformer kind of thing, right? Like, and the language model can be a pure.
It might be something in between, because language is kind of in between, right? It's not
right.
So I don't know. I mean, so I think so. It might be it might be. So that's kind of that's a bit where my kind of if you ask me my sense on this, not looking into that so I think it's definitely interesting because there are these domains where you might. Like I said, if you're doing audio, you still might need these kind of stuff because you might refer back to like, things which are long previous in the conversation, which are a while back or something like that. So,
yeah, fair enough.
My question would be, what do you think, how important is the argument that transformers are not Turing complete? So is it accepted like it, so it must be dead end, or is it not so dramatic that you say, okay, whatever the problem, we can find data sets and large enough transformers so that we can solve the problems at hand?
I've been actually like if we want AGI, like it's whatever. Thank you. Like what I think it's whatever you describe for yourself as AGI. Like for me, I think it would be important if it would be Turing complete. So I know that like it can perform any algorithm, but it's some people say like, why would you even need this if like we can do like I discussed it also with some of my friends, and some of them told like, why would you need it? Like if you can just have like more tools, you can do RAG, and like when doing RAG is kind of a solution for having this like infinite stripe and having Turing completeness. But actually, the not interesting thing there is that it's you who need to do all of that. And if you want like AGI, we want it doing it itself, and to do it itself, it should be like smart enough. But I don't know. Actually, I was very surprised when I saw somebody talking about Turing completeness like nowadays, because I felt that it's something a bit ancient, something people do memes about, like PowerPoint is Turing complete or something like that. But actually, it's like Turing. It's interesting thing that Turing actually, this Turing completeness thing, he wanted to like program a person, and like by doing artificial intelligence, we want like also do like make a human being, and it's kind of related, but I don't know. I don't have like yes or no, but like for me it's more yes, and I would be happy if we had something like that. And but also we also have always the statement, if we even want AGI or Turing complete stuff in our lives, maybe we don't need it to be happy.
I mean, your printer PostScript is a Turing complete language. I'm not sure that be able to. You're saying that be able to print. A printer is Turing complete, but that doesn't necessarily mean it's going to be. It's very smart. So.
Yeah. Actually, yeah. Maybe if thinking about that, like. To program a human, like not every human can like do all these algorithms. I don't know, like it's. I think this AGI thing is very personal for every person, like who, what you consider for yourself as this like AGI. So I think for a lot of people, like a lot of people think that LLMs are already AGI, and it's like enough for them to be fascinated and convinced. So. Yeah, maybe it's not so important.
Any other questions? Thank you so much.
Will you share your slides later, Alina?
Yeah, sure.
Nice.
Great. And with both slides and recording.
Yeah, thank you very much, everybody who saw that.
Thank you.
Thank you, guys.
Thanks, very interesting.